You wish to play a game where there are 6 envelopes. 2 of the envelopes have a dollar bill and the other 4 are empty. For the game, you choose 2 envelopes and you get to keep their contents. What price would need to be charged for this game in order for it to be fair? And how would you modify the price to ensure that the house gains an average of 10 cents each time the game is played? Alright, so if we want this to be a fair game, that means we basically need to know, we're talking about the expected value. So let's look at this as from the perspective of what's the expected value if we didn't have any cost to play this game. That seems like a valid amount to charge. So let's see. When you play the game, you choose 2 envelopes and you get to keep their contents. So let's think about what our random variable should represent. And to me, it seems like we're talking about being able to keep the contents. These are each dollar bills. I would say X should be the amount of money you're winning, or your profit. Well, I'm just going to call it the winnings here. So your winnings, you could get both envelopes where neither of them have a dollar bill in them. You could get one envelope, or you could get both envelopes where they have a $1 bill in them. So your winnings could be 0, 1, or $2. Alright, to figure out the probabilities here, we need to think about the different ways we compute probabilities. This is definitely not binomial. You know, when I'm kind of considering binomial my first check. If yes, then yay. That's supposed to say yay. If we're doing a binomial problem and we see that it's binomial, then there isn't really much to do, or at least we have a lot built into the binomial distribution. We can kind of plug that into the calculator. The only other real counting technique we've seen in this class, or the only other way to find these probabilities, is to use our counting techniques. So this is why I would then look to see, okay, is this with or without replacement? And then I would say, let's see, no or yes. If it's with replacement, then this means we're going to use our multiplication principle. If it's without replacement, then we have to then ask, okay, what about order? Let's say no, yes. This is a weird organization for this chart. If order matters, we're dealing with a permutation. If order does not matter, we're dealing with a combination. Alright, so in this instance, we're not dealing with a binomial. This does not have replacement, because when we're picking an envelope, we're not going to put it back and just to pick it again, so this does not have replacement. And asking the question of order, does it matter if I choose the envelope, let's say I'm in this instance right here, does it matter if I choose one that is empty and then one with a dollar bill, or if I choose the dollar bill and then one that's empty? Those don't matter, so we're dealing with combinations here. Alright, so now that I know we're dealing with combinations, we're going to have to do the N of E over N of S to find the probability here. And let's see, we're choosing 2 envelopes, so from the there are 2 envelopes have a dollar bill in them. So from the 2 envelopes that have a dollar bill, we're choosing 0. From the 4 envelopes that are empty, we're choosing 2. Over 6, choose 2. If we in the instance where we get exactly $1 bill, then from the 2 that have a dollar bill, we're getting 1. From the 4 that don't, we're getting 1. And over here, from the 2 that have dollar bills, we're choosing 2. From the 4 that don't, we're choosing 0. These numbers I can actually figure out pretty easily. 6. This is 1 times 6. 6 choose 2 is, I don't know offhand. 6 choose 2 is 15. 2 times 4 is 8 out of 15, and 1 times 1 is 1 out of 15. So those are my probabilities after I simplify them. Okay. We're trying to figure out what the expected value is, so that's why we're doing this. So 0 times the probability of 0, plus 1 times the probability of 1, plus 2 times the probability of 2. That one is 0. Okay, 1 times the probability of 1, that's just 8/15. 2 times the probability of 2, that's going to be 2 times 1/15, or 2/15. That gives us 10/15, which is, what, 67 cents? 6.6 repeating. So the expected amount of money you would get out of this game is 67 cents. So I would say the cost to make this a fair game would be 67 cents. This would be, let's see, what is the price that would need to be charged? That is the price that would need to be charged. How would you modify the price to ensure that the house gains an average of $1.10 each time? So usually this is a very common thing that's done. You'd figure out what the expected value of playing this game and expected winnings of the game would be. And then you'd say, okay, well, I don't want to break even on this if you're going through the effort of letting people play this game. You'd say, okay, instead of charging 67 cents, I'm going to charge 77 cents to ensure this is fair game. Maybe I shouldn't have crossed that out. This one is fair game. And this one is a profit of 10 cents. Expected profit, that is. Expected profit of 10 cents. You can see they just charge an additional 10 cents, and that allows them to, on average, say that, yeah, every time somebody plays this game, they will be earning approximately 10 cents.